depois eu passo o microfone para você. Thank you, everybody. Next speaker is Dr. Devendra, that will talk to us remote from India. And I just imagine that it's very late in India now. So let's call him. Hi, Devendra. Good evening. You can hear us? Yes, if you can hear us, just say it with your hand.
Yeah, I can hear you.
Yeah, we can hear you too. The sound is good. Thank you for joining us. Thank you for being wake up until this time. And I will pass the word for you. And if you can share your screen, we will see your presentation.
Yes, I will.
And you have 30 minutes. You can. It's okay.
Can you see my screen now?
We can see you.
Okay.
Very good. Okay. And you have 30 minutes. When it's 10 left, I will give you an advice. Thank you very much. And go ahead, please.
Okay. Thank you. Okay, so thanks a lot. And first of all, let me thank the organizer for giving me opportunity to deliver this talk. So in this talk, I am going to talk mainly about the multi-wavelength astronomy activities, which is currently carried out in India. So, and different institutions, of course. So basically, multi-wavelength astronomy in India. So we have been doing research on wide areas of astronomy and astrophysics, such as solar and stellar seismology to star formation, and time domain astronomy has been one of the important research activity in India. And more recently, we have started working on exoplanets and, of course, gravitational waves, as well as pulsars using radio observations and so on. And also, we give a lot of emphasis on building astronomy instruments, for example, like UV, optical, and X-ray, and infrared, and of course, radio using GMRT. And also, Indian astronomers have vibrant science and instrumentation collaborations on the ongoing and upcoming projects like our own GMRT, LIGO, SKA, TMT. Also, we are partner of TMT, and Aditya L1 is the solar mission, which is going to be launched in next year. And also, we have been doing a lot of instrumentation activities for Indian ground-based telescope, like 2-meter Himalayan Chandra telescope and 3.6 Aries telescope, which is the largest telescope in India right now. So let me give a brief, summary of different activities. I will start from a shorter wavelength to the longer wavelength. For example, in X-ray astronomy, I think Dr. Kanaksa has already talked about AstroSat. So I just want to say that AstroSat was launched in 2015 September, and it has already completed 4 years in orbit. And actually, 3 main instruments of AstroSat actually fabricated in our institute in TIFR Bombay. And right now, laboratories and payload operation centers are both engaged in helping students and postdocs to analyze AstroSat data and write proposals and directly. And also we have payload operation centers which are distributed in different Indian astronomical places, like IUCA is one of them. And in optical and infrared astronomy, which will be basically the largest group in right now in India. So I am basically focusing more on observational activities in India. So optical and infrared astronomy activities are basically done using facilities which are mostly located in northern part of India, where we have 2 to 4 meter class telescope right now. And also we are going to get new 2.5 meter telescope in the western part of India called Mount Abu observatories. And also we have 2 meter telescope at IUCA, which is close to Bombay near Pune. And also we have famous 2.3 meter telescope or Venu Bappu telescope, which is located in the southern part of India. Of course, we have better sites in the northern part of India, from where we do a lot of optical and infrared observations. So this Indian Astronomical Observatory has been the main activity center for optical and infrared astronomy. So this observatory is located at an altitude of 4,500 meters, very close to China border in the northern part. And since this part is dry, so we get almost throughout the year, we basically carry out observations because there is no monsoon rains in this part of India. And this observatory has basically hosted 2-meter telescope called Himalayan Chandra Telescope, which has been the major workhorse for last almost 2 decades, which is a 2-meter aperture telescope, and it has basically one main focus, basically the direct focus, and then it has 4 side ports. So we can actually do near simultaneous observations in optical and infrared in the same night using this telescope. That's why this telescope has various optical and infrared instruments which are located. Only that this telescope is basically remotely operated from Bangalore center, because it's very difficult to go for observation at such an higher altitude observatory. Of course, there is a local star which is actually located in this place, which basically they do the operation and maintenance of these facilities. So most of the observation, done by these telescopes were in the area of time domain astronomy, basically to study various kind of transients like novae and photometry and spectroscopic of supernovae, and also afterglows of gamma burst sources. And more recently, we are basically looking for electromagnetic counterpart for gravitational wave sources using these facilities, and also fast transients. So these are some of the activities which have carried out by this telescope. And since this transient basically events have become very important, particularly when we have alerts from like IPTF, Palomar Transit Factory, and so on. So in this place, now we have set up one robotic telescope called Growth India Telescope, and this has been used for remotely observing these kind of transients like supernovae, gamma ray burst, and of course electromagnetic counterparts of gravitational wave sources. And Growth is basically an international project led by Caltech, and this is basically one of the chain of Growth telescope which has been recently installed last year and used for study the transient sources and follow up of these kind of sources. And the next facilities we have in a slightly lower altitude at around 2,500 meters called ARIES, Aryabhatta ARIES Institute of Observational Sciences. So this facilities has now the largest telescope in India, which was installed in the 3.6 meter telescope installed in 2016. And also this facilities has 1 meter class telescope which has been used for a lot of follow-up observations of various kind of transient sources and variable sources. And so research activities in ARIES are basically carried out mostly in star cluster and star formations, and also on extragalactic areas like actigalactic nuclei, GRVs follow-up after flows, and also quasars and so on. And this is just one example where a lot of variable sources has been basically discovered by these facilities. For example, NGC 6866 is one example of open cluster where new classes of variables were discovered by using long-term observations using facilities at ARIES. And more recently, astronomers are basically using these young emitted sources in star-forming regions to find out the pulsating sources around young star like T-Tauri stars and variabilities around these stars. So this is one of the activities using these facilities. And afterglows of GRVs and supernovae has been a very strong activity, basically follow observations using these facilities. For example, the data from these facilities has helped in constraining the light curve properties like jet break energetics and the spectral energy distributions, and this has basically helped to basically pinpoint the physical parameters of these events. And so far, more than 2 dozens of such kind of sources has been studies using ARIES facilities. And more recently, people are basically following up of these transient exoplanet sources, basically to constrain the nature of these sources once they are discovered by Kepler or, for example, WESP surveys. And so basically brighter sources. So for example, this is one example of WESP 12, which has been followed up by these facilities, where you can see the flux variations of 17 millimagnitude using like 1 or 2 meter class telescopes. And these help us to constrain various physical parameters of exoplanets. And also a lot of activities were done in AGN and Bejar variabilities, where long-term systematic studies, for example, like intra-night optical variabilities and intraday and long-term variabilities studies were done. And these kind of variabilities and different time scales allow basically to understand their environment and energy generation mechanism in the central engines. So different kinds of these AGNs have been studied by various groups like BL, LAC objects, FSRQs, and QSOs, and so on. And of course, star formation in around young cluster has been very strong activities in various centers in India, basically using multi-wavelength data using 1 meter class telescope, and now we have a couple of 2 meter class telescope, and more recently 4 meter class telescopes, and many star forming regions have been basically studied in multi-wavelength regimes using these facilities. So now I will touch upon slightly about infrared instrumentations. Of course, optical astronomy has been the main areas for last many decades in India, but more recently in using this new class of telescopes, a lot of infrared observations have been carried out, and to carry out in multi-wavelength regimes, we needed basically dedicated infrared instrumentation activities. So this has been basically started more recently in India. So basically, infrared astronomy activities were mostly carried out in our institution in TIFR in Bombay. So we have been doing infrared instrumentation not only for ground-based Indian telescopes, but of course for space-based platforms like balloon-borne observations, which has been basically carried out in India for many decades in X-rays and far infrared. And also we have a lot of good opportunities to do basically to develop instrument for our satellites. Like AstroSat was one example for UV and X-ray, but we also have proposals for infrared experiment using satellite-based platform using our space agency. So I will just give you some example on instrumentations. For example, this 3.6 meter telescope, which is a new telescope and largest telescope in India. So various kind of optical instrumentations were done, like imagers and spectrographs have been developed in-house for this telescope. And also we have a couple of infrared instruments which has been recently developed for this telescope in-house. And one of the important instrument, which basically imager, which was developed basically in Bombay, was this JHKL instrument. Basically, of course, JHK observations we can do with basically like mercury cadmium telluride kind of detectors, but this instrument was developed using indium antimonide detectors, and basically to observe beyond 2 micron, like in L band. Basically, the aim was to study the pH features at 3.3 microns in star forming regions using these kind of instrument. And basically this instrument was developed considering the very good site, for example, where this instrument telescope has been installed. For example, if you see in this slide, we can have a best seeing of the order of 0.5 to 1 arc second from this site. And basically it is in K band, and basically this allows us to basically detect photons in L band, which is at 3.6 microns. So we can actually detect L band sources from this site. And of course, the altitude of this site is only 2,500 meters, but we can actually detect sources up to 10 magnitudes, 9 magnitudes in L band from the site. And this basically encourages us to basically observe in longer wavelength than K band, which is 2 micron. And that's why we have actually observed pH emission in one of the star forming region using this site, which is just at 2,500 meter altitude. So we can see that sky brightness in this site is comparable to the best site in the world. And that's why this encourages us to develop instrument which can operate beyond K band. And since we have a lot of optical and infrared astronomers now in India, so there was a demand to develop a instrument which can simultaneously observe in optical and infrared wavelength. So we have actually developed more recently a state-of-art instrument which can simultaneously observe from 0.55 to 2.5 micron band, and this is basically using the infrared detector, which is mercury cadmium telluride. And so this basically gives seamless coverage from optical to infrared, and we get actually typical resolution of the order of 2500 in cross disperse mode. It has two modes of operations. One is cross disperse and another is prism mode, which gives us resolution of 100 to 350 from J to K band. And so this is the advantage that you in the same night you can have a simultaneous observation. So this is one example where in the right hand figure we have this free spectral range where we can see from GMAX modeling that this instrument can operate from 0.55 to 2.5 micron. And the left hand side we have the first light image from TRISPEC just in April this year, where we can actually achieve in lab basically the coverage from different orders from optical to infrared wavelength. So this instrument now is in a commissioning phase and will be available worldwide community through proposal peer review proposal system from the next cycle, which will be after October, after this monsoon. Currently we have a monsoon period, and then after November next cycle will start, when this instrument will be available to worldwide community for optical and infrared observations. And then I will move on the far infrared astronomy, which are basically carried out using balloons in India for many decades. So right now our main activities is basically using 100 centimeter balloon bound telescope, and the focal plane instrument which we are using is Fabry-Perot spectrometer, which is tuned to 158 micron, which is basically to observe singly ionized carbon line to study the photodissociated region in star-forming regions. So we have a strong Indo-Japanese collaborations where basically from astronomers from JAXA and Nagoya universities are basically developing detectors, and we have actually developed our telescope, and this telescope can give you the resolution of 1 Archimedes based on the diffraction limit of these telescopes. And using this telescope we have been basically observing a lot of photodissociated regions in C2 line and 158 micron for basically last 1 decade or so. So far this telescope has been launched 26 times, and we have observed several star-forming regions in the galactic plane of our galaxy. Now, next is radio astronomy. Of course, our major workshop in radio astronomy is our own GMRT, which is basically operating from since 2000, early 2000, and it has a 28, basically 30 antennas. Each antenna has 45-meter diameter, and it can actually observe from low frequency like 130 megahertz to 1.4 megahertz. So one can actually study not only the continuum observations, but one can also observe in neutral hydrogen at 21 centimeter, as well as one can actually study the radio recombination lines. And so we can do range of sciences using GMRT, for example, from sun and extrasolar planets to cosmology. And more recently, GMRT has been upgraded fully. And so you can see here in magenta color, these are the now wide range coverage, which has been basically developed during this upgradation phase, where this rectangular in blue color shows the old GMRT and magenta in color shows the upgraded GMRT. So we have now seamless wide coverage using upgraded GMRT, and this allows us now to increase our sensitivity. For example, broadband coverage can give significant increase in redshift space for H1 lines, and continuum imaging sensitivity has been improved by a factor of 3 or more. So in this panel in right hand side, one can see these magenta colors are basically upgraded GMRT sensitivity, and the blue points are the old GMRT. So one can clearly see that now this upgraded GMRT is compared to other major facilities like early phase of SK observations, and this allows us to now to do the sensitive observations in radio domain. Now I will go to the science part and mostly concentrate on my own interest on star-forming regions, basically multi-wavelength studies, which we have been doing in many different groups in India, basically to study the massive star-forming regions in multi-wavelength wavelengths. So as I explained you, we have various facilities now in India, optical and infrared telescopes, radio telescopes. So we have been basically using these facilities to study these galactic star forming regions, as well as outside facilities through basically our collaborators within the BRICS. For example, like we have a strong collaboration with our Russian counterparts, where we are using the molecular line observations, and here we are using the radio observations. So one of the problems which we have been studying basically the formation of massive stars, which has been quite puzzling, that how these massive stars are formed. And the problem in massive star formation is that these stars are basically burn hydrogen while still deeply embedded in natal cloud. And then they also have strong feedback effect like radiation pressure and photoionizations. And so observationally, it's difficult to observe these sources. So of course, we know various mechanisms where we can form the massive stars. For example, like coalescence of low mass stars in a dense cluster environment where we can form the massive stars, or by competitive accretions. But more recently, one of the very important aspect of massive star formation which has been discussed, and observationally there are proofs now that do cloud-cloud collisions trigger high mass star formations. And of course, theoretically, it has been shown that like Harvey and Anand Pindika, that cloud-cloud collision basically induces the formation of cloud cores by enhanced cell gravity as a consequence of shock in compression. So for example, in this cartoon, you can see if you have two clouds, one is a small cloud and the other is large clouds, when they are moving around each other because of the shock when they are colliding, you can see because of shock a complex layer, and with the time, with the gravitational instabilities, these can actually form the dense clumps, and with the time evolves, they can form the high mass stars. And this is one of the topic which has been now discussed, that possibly this is one of the scenario where you can form massive stars. So similarly, a lot of simulations have been done to basically prove this scenario. So this is one example of magnetohydrodynamics simulations where these are basically, these cartoons are showing the surface density plot in CO line observations. So for example, the first figure here shows the before collisions. These clouds are basically prior to 10 kilometer per second kind of collision. This is the typical velocity which they are moving. And after collision, you can see the snapshot here where a small cloud has merged to the larger clouds. And in the third figure, you can see the position velocities plot, where you can see basically that there is a small cloud which has merged to the large cloud, and in between you see an intermediate velocity feature which is called the bridge feature. So this is a typical scenario where these cloud-cloud collisions are happening, and these are the signatures which can tell us that in that areas one can actually form the massive stars. And this is another scenario where as per observer, basically this larger cloud is red shifted and the smaller cloud is blue shifted, and this yellow color you see the intermediate velocity features which can actually give you the bridge features in the position velocity diagram of molecular line observations. So this has been now basically confirmed that these kind of scenarios can form the massive stars, and typical signatures of these are basically bridge features at the intermediate velocity range. And also you see different complementary features like formation of young stellar objects around these areas where massive stars had formed. And so recently we have carried out such observational studies in many such S2 regions where this cloud-cloud collision is happening. And this is one good example of our BRICS collaborations, where with collaboration with Igor Zinchenko from Russia, we have basically done the multi-wavelength studies of these S2 regions to see these kind of cloud-cloud collisions. So I am just giving one example of cloud-cloud collision. So this is basically, okay, thanks. One example of bubble called N49. This is the mid-infrared bubble which we discovered in Spitzer observations, and by Churchwell and Atoll, one can see these kind of bubbles. And this is basically ionized, this bubble is ionized by an O-type stars, and the idea is that basically how this O-type stars has been formed in this around this bubble. So here one can see this multi-wavelength view of this bubble at different wavelengths. For example, like 8 micron, one can see the pH features around these bubbles, and one can go to the 24 micron in the last figure where red contour shows the ionized emissions. So basically, ionized emissions tells us that there is a Lyman continuum photons which can be basically generated from O-type stars. So there is a O-type stars. So we are looking for the formation of this O-type star. So this is the example where we see the molecular cloud. So this is the dust cloud in Herschel band at 250 micron, and one can see these elongated filamentary features. For example, different elongated filamentary feature. At the interface of this, we see this bubble which is located. So naturally, because of this collision of filaments, this bubble has been formed, which means this young star, massive stars have formed. So in the basically in the velocity plot in molecular line, one can clearly see different molecular clouds which are intersecting around these filaments, and at the intersects of this filament where this bubble is situated. And if we just see now the position velocity diagram around this bubble, for example, which is called region 1 here, one can clearly see two clouds which are colliding, and in between we have an intermediate feature we call bridge feature, which is basically the signature of cloud collisions. So basically similar kind of signatures we have seen in many H2 regions. So together, I can say that these observational results suggest that in this bubble or other H2 regions, the collision of filamentary molecular cloud appears to operated basically a few mega years ago, and may basically trigger the formation of embedded protostars and massive stars, because not only massive star, we can also see protostars around these regions, which has basically formed by the interaction of these filaments. So we have basically argued that cloud-cloud collision could be a major mechanism of high mass star formation. So this is just a summary that access to astronomical facilities outside India through BRICS collaboration will greatly complement and basically expand the scope of Indian programs, and we are looking for these kind of collaborations. Thank you very much for your attention.
Thank you, Devendra. Now we have time for a few questions.
Thank you.
David.
Hi, Devendra. It's David Buckley speaking. I'm just interested in the optical infrared spectrograph you were talking about. Is the whole instrument cryogenic?
Sorry, I can't hear clearly. So.
Sorry, I'll say that again. For TANSPEC, the new IR optical spectrograph, is the whole instrument cooled? Is it a cryogenic instrument?
How this range was expanded, basically?
No, I was just asking, is the whole instrument cooled?
Actually, voice is not very clear. So, can you? Yeah.
Let me put it again. Is it cryogenic or works at room temperature? Is it cooled, cryogenic?
Yeah, okay, I can hear. Yeah, so it's basically the hybrid system. So it has basically, we are basically using the cryocoolers, helium cryocoolers for the cold plate, and then we also using the liquid nitrogen. So basically the outer part is cooled by the cryocooler, and once we reach the temperature of 130 K or so, then we are using the liquid nitrogen to cool the inner divar.
Thanks.
Any other question? No. So let's thank Devendra again for participation.
Thanks a lot.
Our next speaker is Chen Zhang.
Okay, good afternoon, everyone. It's a pleasure to be here to make a brief introduction of the Proper Mountain Observatory optical networks activities. Okay, this telescope network originated from the first man-made satellite supporting mission. Okay, then it started systematic operation from the China's first satellite mission in 1970s. Then it starts technical modernizations around around 2000. Now it is the largest civilian optical network in China, which many aims at the Earth's orbital environment researches. For now, we have 7 sites in operation, but we will have more sites, about 6 sites for now under constructions. We will have more telescopes in these red sites. So for now, we are operating 19 sets of dedicated facilities with more than 250 tubes for space debris at the 8th site. Okay. I'll leave it. We are developing new type of facilities for survey or characteristics research besides the conventional tracking telescopes. We're maintaining a catalog of all kinds of space debris, including orbits and light curves. And we run a data center for data collecting, track relating orbital determination, prediction, and conjunction analysis. We also have a research group for the image, the data reduction, improvement, and for the observation strategy optimizing. This is the we have several subsets of the telescopes. This is the tracking facilities. We have several telescope, Newtonian telescopes, and refractors for LEO tracking. Also, we have several larger telescopes for MEO or GEO tracking. This is some of the telescopes all over the country. We're doing the closed loop tracking when we observe the faster moving objects. So the moving objects detection while in waiting state using the morphology, then use the closed loop speed guidance based on the center offsets of the targets. We will use the fast astrometry and the photometry calibration with star prediction. So the data will be reduced in real time. So this is the main processing pipelines of the data. Also, then we start doing the to find the new objects using the survey telescope. So this so also they have the survey telescope for LEO and the survey telescope for MEOs. For LEOs, they are fixed telescopes with multiple tubes. So here we can see several sets of the optical telescope array, which covers the low altitude ring to observe as many as possible LEO objects. Then we have the Then we have the several larger telescopes that can survey specific field for objects that are moving more slower than the Leo. They can cover the field that we specified. Okay, this is the symbol of the optical telescope array. Because in old days we can only have the full frame large. We use large format CCD cameras, but it is full frame. So, but we also cannot use the mechanical shutters. So there are smears when we do the observation. Because when we read out when the camera read out the images, it is also received signals from the objects. So we develop a whole new algorithm to do the pre-reduction of the image, and we use the GPU accelerated to fulfill the scanning for the full field scanning in real time detection. This is about the 2009. So it's very earlier that use the CUDA technology. Also, we developed some special type of telescopes for. Yes, this is the for the observation. This is the quarter channel telescopes. For the first stage, it is the synthetic aperture designed to gain the profit of the both large field of view and the deep detection, because in those days the EMCD camera has only small area, so we have to use the small telescopes to gain the large field of view. We use the multi-camera synchronized triggering technology to take 4 images at the same time, and using the real-time image stacking benefit from the faster image registration and the CIC reprojection method. We can do the stacking 4 frames in 5 milliseconds. So we can extract the objects in real time and do the closed loop tracking. This telescope was also the prototype of massive coaxial cluster telescope cluster. This is the fastest stacking method. We use the star position estimation to accelerate the calculation speed, then doing the image registration, doing the reprojection, and then add them together, so it can be do very fast. This is the brief pipeline of the telescope. After that, in order to meet the requirements of the synchronized multicolor photometry, because space debris luminosity will rise rapidly, so we add different filters on quad-channel telescopes. This is one of the malfunctioned satellite from India. We can do the multicolor photometry using this telescope and find the variation both in the luminosity and in the color index. For now, we are trying to add synchronized polarimetry systems to do more, to get more information from the space debris. This is the most recent telescope array called CHESS. It's a rapid optical survey telescope array. For first is an extension of current optical telescope array design, but it has multiple scientific goals design. So we split the survey in multiple levels and control all the survey observation in one system. This is the general survey subsystem. There are 12 28 centimeter refractors with 7 degrees. With 7 degrees, and the pixel size is about 8 arcsecond. The whole system can cover 600 degrees square degrees in one exposure, so we can use this system to do the all sky survey. The magnitude limitation is about 17 in G band, Gaia G band in 4 seconds, and 17.5 magnitude in 60 seconds. The other system is the other part is the deep survey subsystem. These are two AZ800 from the ASA company. It's a prime focus design and using the Andor cameras. It's a 2x2 square degrees and 1.7 arcsecond per pixel. This telescope is used for the following ups and deep survey for the different kind of objects. The limit magnitude is about 18 and 19.5 magnitude in G band. Also, we developed a small all-sky subsystem, all-sky monitor subsystem. It's a small fisheye telescope, which can cover all the visible sky. The limitation, the magnitude limitation is about 1260 seconds exposure. So we can use this telescope to observe the stars instead to make the judgment of the weather and the observation conditions. So we can use this information to guide the telescopes to avoid the area with bad weather. Also, this data can be used to detect the fireball events and other events. For the phase 1, we're only doing the geo survey from the 40 to 160 degree. This is the area we survey, and this is the geo objects that we detect. The detection is down to 70 magnitude and cover most of the catalog of the geo objects. This is the brief pipeline that we detect all the moving objects. So in one field there will be 20 to 30 objects that we can detect. This is the objects that we can detect for one night. In phase 2, we will run geo survey 1 time per hour, cost 60 minutes. Then we use the other time for the all-sky deeper survey. We will observe one field. We will use 1 minute per field and half an hour for one round to cover all the sky about 25 degrees. The exposure spread in five frames, 4 10 seconds and 1 second frame. This is used for the fast moving objects detection, and then use the stacking to get more deep image, to get deeper image that can be used for the astronomy research. So the science can cover the GRB detection or asteroid detection of variable stars. This is the main pipeline of the Earth orbital objects detection using this method. So we use this method to remove all the stars and makes the space debris only left on the image. Then we use the stacked images for transit event detection. This is the pipeline. It involves the template requirements and the transit detection using the image difference technology. So with this, we can we spread the sky areas into multiple areas. So the research based on the network it's the observation technical development and the application with the orbital data, including the cataloging, prediction, conjecture analysis, atmosphere modeling, and the re-entry prediction, and the photometry and the physical characteristics analysis. Based on this data, we can do dynamics research by including the geo evolution, long-term orbital dynamical evolution of the ammonia type, and the rotational motion of the space debris research. But except for the space debris, we can do more with these telescopes. First is the asteroids research. We can use from our images. We can have more massive detections from the data archive. They can the images covers many can produce many detections, and with this we can find the new objects and doing the follow-up of known objects. Also, we can have the light curve observation with our telescopes. This is the recent observation of one binary asteroids. This is the archive. This is the archive of the light curves. But recently, we use our telescopes to complement some of the light curves, some part of the light curves to make a more complete light curve to determine the initial values of the parameters. This is the simulated. This is the simulated shape of the asteroid. Also, we can use our network to do the solar system objects occultation observation. This kind of method can provide a high spatial resolution compared to the deep space probes about several kilometers. Measure the size, and it can use to measure the size and the shape of the SSO, and the probe for the secondary objects and the extended structures of the objects. And also it can use for the high precision astrometry of small SSO with small telescopes. We just detect the signal that an asteroid blocked the light from stars. So the occultation requires the telescope has the high speed cameras to get as many samples as possible in the duration of several seconds to a few minutes. A typical event is about 1 minute or even 10 seconds. We need a larger telescope to get more events at a certain level and accurate timing. Also, the problem is about the size, because the occultation only occultation events only can be only observed in a belt. Just show like this. Only telescopes in this belt can do the observation. So we want to have more telescopes that can detect more events. So the tracking subsystem of our network is suitable because we have EMCCDs, we have multiple sites, and no needed side tracking for the telescope. This is a typical light curve of the occultation. This is the sum of the occultation test using our telescope network. And recently, the Pluto occultation is a very important event that can be observed. Also, we can use this data for the transit detection. The time domain astronomy group of the Purple Mountain Observatory, they develop a system for our telescope network to receive different kinds of event signal events, and make the scheduling of our to do the survey, the discovery, and the follow-up of these kind of events. This is the we can get a notice from the GCN and calculate points with no galaxy positions, and make the scheduling with a special algorithm to make the observation list. Then plan the observation parts of the for the efficiency. Then we were doing the data processing based on the pre-reduced images. And finally, we will reject all the NEOs and variable stars, and using the machine learning data sets to find the most reliable candidates. And finally, the candidates can be reviewed by human. Also, we have one telescope, one 80 centimeter telescope in Yaoan site. It's not belongs to us, but we can use this telescope for the follow-ups. And this finally we can do the circulate. The future plans. The future plans. We want to expand the network physically. We are trying to set up telescope in South Africa, in Brazil, using the optimized 280 millimeter telescopes with a smaller field of view and better performance. Also, another system with the right fast 400 for the tracking. Optionally, we can use the containerized telescope cabin with roof and the solar panel and the shipping capability. So it can it can be distributed very fast. But moreover, with our BRICS organization, we want to expand the network gradually. We are trying to develop a logical layer of a network that connects all the telescopes or telescope network. It will implement a common input for different scientific goals with the human computer interface, GCN or databases, and the common output for scheduling different telescopes dynamically. So we can use a larger visual telescope network for doing all these observations. Okay, thank you for your time. Yeah.
Any questions?
You have this project for monitoring space debris.
Yes.
Russia has a similar program, and Brazil, to a certain extent, is also involved in that. Do you consider, so that would be an obvious project for a joint project within the BRICS. Did you consider that, or, and here Liberty might also want to comment, do the governments consider that project too sensitive to share the data?
I believe that in space debris research, it will be it can be implemented international cooperation, because under the coordinate of IADC, all the space debris research can be shared. No, for space debris, there's maybe some part of the work can be done between institutions. No need for the national permission, I believe.
Which group in South Africa are you talking to?
We're talking to a private company.
Not the South African Space Agency?
No, we are because there's I don't know why, because but we find a university professor that can help us to do the operation of the site.
And where would it be?
Maybe near the Cape Town. Yeah.
I'd be interested to know who you're talking to and what group it is.
Okay.
Yes. So thanks a lot, Chen. And I mean, the three presentations in this afternoon are interesting because they talk about telescope networks that are existing already.
Yes.
So I think it's interesting to look, it's a general comment, yes? It's interesting to look at the experience of these networks and the points that you made of improving them through virtual connections and and virtual layers of logical telescope connection for using that maybe as a pathfinder or some kind of initial attempt to create a transient network for the BRICS that can work and show results fast, and then can motivate bigger projects on transient network. So we saw a flagship proposal on transient network, but maybe there is something which we can deliver through all the countries with existing networks. So I think this is an important point. And maybe the only thing that's needed is information technology to make this happen now. I don't know if someone wants to comment.
Okay. Yes, because we don't have to wait for the hardware constructions, and we all for now we are cooperating with Esta. They also have the multiple telescopes all over the world, so it can be there is already a large telescope network. What we have to do is on the software level, so we can make the scheduling more efficient for the joint network, right?
Okay, I think we try to keep on schedule. So if someone wants to speak to Chen Zhang again, let's go for the coffee break, and then now it's Igor Molotov before your turn. Yes, now.
My presentation is similar to previous. It's also about large network of telescope, but some more scale masштаб, global network. The name of our project is ISON, International Scientific Optical Network. Our project started in 2004 year as open international voluntary project to cover 3 main scientific areas. First is space debris, under coordination of our Institute Keldysh, Institute Applied Mathematics, Russian Academy of Science. Or asteroids topics, jointly coordinated with Institute of Astronomy of Kharkov National University, Ukraine, and again Keldysh Institute of Mathematics. And third topics is gamma ray burst afterglow, optical afterglow, under coordination of Space Research Institute of Russian Academy of Science, Alexei Pozanenko. During our project, many tens telescopes were produced or modernized. Currently, 28 observatories with 55 telescopes, different aperture from small 18 centimeter to 2.6 meter, cooperate with our project. Telescope building is the pictures with telescope produced under our project, different class, from small telescope 12 centimeter to large telescope, respectively large 65 centimeter. Is a series of telescopes. Also we attempt to adjust producing of mounts, domes, pavilions, focusers, etc. This is mounts of our own production. 40 centimeter telescope, 50 centimeter telescope, different class telescope, mainly with large field of view, but also some telescope have reasonable field of view for tracking. Is pictures of telescope and observatories which cooperate with our project. Of course, significant part of this telescope, not our, is owner of institution, of some private telescope, observatories, but we have agreement about cooperation who submitted the scientific proposal to obtain some observation time for our scientific goals. And the different color is different class telescope, different color, yellow is survey telescope, blue telescope for small telescope, very large field of view to obtain precise orbit for geostationary object. Green telescope for follow-up of bright object is small 25 telescope class, and this color is telescope for a follow-up of faint object is 40 centimeter, 50 centimeter, 80 centimeter. And this color is telescope using for asteroid observation is more large telescope in ice and cooperation up to 2.6 meter in Crimea. A few words for introduction of space debris. You know, is quantity of space debris is growing dramatically. Therefore, scientific space debris is unique research object because it's crossed interest of different aspects. Is interest of science, because yes, space debris has anthropogenic or is man-made origin, but now this space debris population developing in own rules with love of nature, and therefore it's necessary to investigate these loves of development of space debris. All these topics of diplomacy, elaboration of measures to minimize space debris origin, this discussion at United Nations level, many hundred countries participate in discussion. All that necessary to elaborate the rules of motion, behavior in space, for which country now is, during last session of United Nations COPOS, it was adopted 21 rules for behavior in space for own countries. All that necessary to determine the scopes of reaction in the case of problem caused by space debris and satellites, collision, re-entry, etc. It all that necessary to think is keep possibility to use space for future generation. It's necessary to minimize, it's necessary, etc. To remove, it actively discussed. Also is the topics of space industry. Protection and security of spacecraft, minimizing the causes of failure of spacecraft, conjectures, assessments, analysis, forecast of re-entry, etc. Space debris research with our project is in Keldysh Institute of Applied Mathematics. In part of observation, we provide global surveying of all geostationary orbits. Our telescope covers all geostationary orbit, and we can, during good night, obtain measurements for all geostationary satellite and space debris. Also, we provide tracking bright geostationary, high elliptical, and medium Earth object, like GPS GLONASS. Also, navigation satellite. And also, we provide searching and follow-up of fine debris object. Is more in our we support the observation of more large Russian cooperation, which included telescope of industrial organization, another telescope of Russian Academy of Science, and also telescope of Russian Space Agency, one from which situated in Brazil. What the goal of our activity? Firstly, we maintain the space debris database for the Russian Academy of Science as central information node to perform space debris research in Russian Academy of Science. Also, we support the orbit catalog of space objects to provide the conjunctions assessments analysis for Russian satellite under contract with Russian Space Agency Roscosmos. And also, we develop the space debris population model at high orbits. Is our model, some pictures. Is our calculation dangerous approachment between active satellites of around the all geostationary orbit with space debris during last year. Green color is the position of Russian satellites. Red color is very close conjunctions down to 1 kilometer. Blue color is 5 kilometers. You can see the conjunctions regularly exist in the geostationary orbit. Also, in principle, the space debris is very interesting. Many hundred interesting objects is real zoo park of some interesting object. Some example, some magnitude is changing very quickly, up to 10 magnitude, some object. Also, we discovered and track during many years 100 objects with high area to mass ratio, up to 50 square meter per kilogram, is less than paper. And real object, very bright, very large, existing in space. He have crazy ballistic evolution under solar radiation pressure. Some geostationary object under solar radiation pressure re-entering into Earth atmosphere is crazy. It real solar sails is a sample of 10 years of orbital plan evolution for one from object we discovered and tracked during many years. Is the quantity of object in CAM database during last few years. Is red color is geostationary object, green color is high elliptical object, and blue color is object at 20,000 kilometers altitude, with GPS GLONASS satellite situated. You can see the quantity of object is increased dramatically, but quantity of telescope not increased with such speed. Therefore, quality of catalog is worse and worse, which during the years. Is why quantity of object increased? Is a simple explanation. Exist explosion at near air object, and this is picture demonstrate for last explosion of American rocket bodies, which resulted in 1.5 time increasing of space debris population with last 16 months. But from it was the detected object, tracked some time, and then lost. Example, in American catalog exists only 100 such objects, such fragments. In Russian, 2,000 fragments, but it's not all. Many objects are lost. Is the answer to question from about space debris is political. Is political sometime, but impossible for one nation to track all objects. Is only in global cooperation maybe solve the problem of tracking of all space debris. And now, in fact, exists cooperation, exists exchange of information with Russian and Brazilian, with Russian and China, Russian and Switzerland, Russian and European country. Some exchange information exists. And now, even during Open Universe Initiative, we discussed the creation of open database for space debris for under United Nations level, because it's a single way to solve this problem. It's the same. Space debris is the topics which may be solved only investigated, only provide comprehensive investigation only during international cooperation. And from our opinion, BRICS is a very suitable body for this work. Why? At least 4 BRICS countries already participate in this work. Russia, China, India, and Brazil already participated in as minimum observation of space debris. It also exists plans to install telescope to track space debris in South Africa, and Chinese and Russian and ICEN project would also have plan to install telescope in South Africa. In this case, all BRICS country will participate in this research topic. Therefore, it may be coordinated BRICS level, because it's space debris topic of science, as explained. And also, all BRICS countries participated in discussion of space debris problem at unit corpus level. And first step of cooperation in this area have already taken between Russia and China, between Russia and Brazil. Next topic of interest of our ISAN project is asteroids. We have the name of our asteroid project is ASPEN, Asteroid Search and Photometry Initiative. Under our asteroids topics, we provide development of survey for asteroids technology using small wide field telescope, which can provide full sky coverage during one night to detect fast near-Earth asteroids, which lost during deep space asteroid survey with large telescope. Also, we provide regular photometric observation campaign of near-Earth asteroids to obtain the data for investigation of physical properties. Also, we provide is new goal for us, but during this year we started providing follow-up near-Earth asteroids with dedicated subsystem of telescope of 35 centimeter, half meter aperture class. And also we try to arrange photometry observation of bright near-Earth asteroids, which year few bright near-Earth asteroids which may be investigated with small telescope, 25 centimeter aperture. We have few tens such telescope, and therefore it's very good opportunity to investigate such bright near. No, one is from work is obtaining MPC code for ISAN observatories, and we already obtained 12 code to the data. Is the list of telescope which participated in ISAN photometry observation campaign. Is telescope mostly 70, 80 centimeter, 60 centimeter, 1 meter class telescope, and even we have few night per month for a 2.6 meter telescope in Crimea. And we have some time for observation in 2 meter telescope in Rozhen in Bulgaria. In average, approximately 250 nights of observation, up to 80 asteroids per year. And we started campaign 2008 year, and up to now we have database about 700 live curves for 300 near-Earth asteroids. Which the goals of our photometry campaign? First is newly discovered, close approaching the Earth, near-Earth asteroid, especially potentially hazardous asteroids, PHA. Near-Earth asteroids, which orbits or bodies characteristic, suggest the possibility of Yorp effect detection. We investigate already known binary near-Earth asteroids with the focus on detection of B-Yorp effect. Also, we provide special search for new binary asteroids. With also studying small near-Earth asteroids with small diameter, which can have very fast rotation. And we also cooperate with radar specialists, and therefore we regularly provide photometry observation of asteroids which are a target for radar observation. Is a sample of our light curves. Is the detection of Yorp effect. It was detected our participation. In principle, what is the good for such kind of research? Why must be network? Because it's necessary to track asteroids with photometry during maximally long time to cover few possible period of his rotation. Therefore, exact network is very good for such kind of investigation. Is search of sample of searching of binary asteroids. We already, with our involving of our data, it seems 7 asteroids confirming York effect, and 8 binary asteroids were discovered. Is a sample of our cooperation with radar specialist. Is the last sample of our participation in observation campaign for asteroids, near asteroids in May. Such quantity of telescope participated in this observation. We provide sometime photometry, astrometry, and sometime in erosion provide also polarimetry and spectrometry observations. Is our project for searching of new asteroids. We have 2 telescopes, 40 centimeter class, with not large field of view. One is New Mexico, such field of view is Australia. Australia joint project with team of Bern University, Switzerland Observatory, and 1 telescope was situated in America, 2nd in Australia, and provide a survey and mutual follow-up. And average we have cover 900 square degree per night with limited magnitude up to 20.5. We obtained more than 1 million. No, firstly, we adjusted our software, we adjusted technical observation, etc. is main result. But we obtained more than 1 million measurements. We discovered 17 near-Earth asteroids, 8 comets, and more 1.5 thousand main belt asteroids. Now both survey hours stopped, and we have planned to restore survey observation with new telescope, which will be installed in Russia. Is Multa, is Altai region, is pavilion, this position pavilion is almost finished. And the telescope is also 40 centimeter, but field of view in few times more is a real CCD image obtained during test observation. Field of view 4 degree for CCD chip, 36 for 66 millimeter, but now we ordered the new CCD camera, some larger, and we will obtain 22 square degree field of view. And also we have planned to start operation maybe November. First test will be with this telescope. But second such telescope is already ordered. We expect that it will be ready next year. And we search the plus with good astroclimate for installation for this telescope. In principle, 4 such telescope will be able to cover with asteroid survey is triple covering for the night to obtain 3 measurements for each object for 2 or 3 nights with magnitude 20.5. Our concept for asteroid survey is using small telescope / field of view. A few steps is these first steps with 2 for 2 degree. Second step is will be now is for 5.5 degree. But now next project exists 50 centimeter telescope with have field of view 7 for 7 degree using the CCD using the CMOS camera, Chinese CCD CMOS camera 61 for 61 millimeter. One such telescope can cover with 3 times per 5,000 square degree per night. We have planned to install 2 tubes of such telescope for 1 mount. In one such double 50 centimeter telescope, one single can cover per night up to 10,000 square degree with asteroid survey. Our opinion is the most inexpensive and maximally quick solution to cover all sky with limited magnitude down 20.5 magnitude. We read some proposal to install 1 meter and more, but for such magnitude. What we believe our solution much more cheap and much more quick. All the part of ICE telescope participated in observation of gamma ray burst optical afterglow, alert and request for observation were automatically received from team of Space Research Institute of Russian Academy of Science. This team then collected, obtained CZ image and provide их processing and analysis. To train our specialist, our observer in this investigation, Space Research Institute, with our support, regularly arranged workshops. We collected tens person and to train in observation technique and preliminary processing of CCD image. Telescope participated in our photometry observation of asteroids, usually also observe in gamma ray burst afterglow alert, but mostly in manual mode. New ICE software for telescope control provide automatical reaction of small and medium class telescope for the JRB alert, and we have planned to widely distribute our software among ICE telescope during next year. We have long history of cooperation with United Nations, and our main result during this June we signed memorandum of understanding with United Nations for cooperation of ISAN with new United Nations initiative Open Universe. It foresees installation of telescopes in developing countries, training of observers, organization of observation, and joint open database at United Nations level. BRICS telescope network proposal for observation of optical transient plus BRICS database. We submitted such proposal, and now we would like to maybe input it to BRICS flagship project with our proposal. BRICS telescope network included ISAN observatory, observatory Purple Mountain in China, and Picos dos Dios telescope observatory in Brazil. Plus, we have plan of installation of ISAN PMO telescope in Brazil, in India, in South Africa, and in other countries. BRICS telescope network will allow the optical observation of various types in integral line and filter, including the simultaneously and few filters, polarimetry, spectrometry, extra wide field observation around the globe. Using our proposal, BRICS cooperation in observation may be started immediately, and our project have very reasonable cost. And for our opinion, our project may be involved in BRICS flagship project. Thank you for your attention.
Thank you, Igor. Questions? Ulysses?
Thank you, Igor, for the presentation. And we have been discussing how to make the things that we do sensitive to the governments and to our countries so that we can get support and attention for the BRICS Astronomy Group. I think space debris is a subject that's very sensitive because the monitoring of space debris involves space economy, because more and more companies start to operate satellites, and they have to know the debris that are out there, otherwise they can lose their satellites. Yes, there is a political level, a diplomatic level.
Two different aspects. You speaking about military satellite. I speaking about space debris.
Yes, space debris.
Space debris is very complicated topics, and many countries forced to join the efforts. It's a good sample, Space Data Association. Many 10 satellite operators joined in the same cooperation. He have joint database, it jointly provide conjunction assessment analysis.
For them.
For them, yes. Therefore, it's time, maybe tens organization jointly work in these topics. Therefore, opposite space debris have not any sensitive aspect because it's topics of science. And all bodies interested in this investigation. All countries participated in investigation of space and using advantage of space. It must be interesting to jointly investigate space debris. And we permanently discuss it at United Nations level. It was group for long-term sustainability in the space. It's a provide aspect of cooperation. And of course, it's very complicated to agree at a higher level. But from lower level, cooperation is already exist. And we discussed about cooperation with many countries. Turkey, with Germany, because they also have joint project invited participate in space debris research in any countries. Even astrophysics project, как называется, испанский проект? Buddhist project also would like to join space debris investigation. Therefore, now we have negotiation with already signed agreement with Purple Mountain Observatory. We started already first step of cooperation. We have joint observation. We have exchange of information. We have similar signed agreement with Bern University. Have joint scientific project. I'm principal investigator from Russian side. And we also exchange of information. We have now discussion with European Space Agency. Our institute regularly sends the data to European Space Agency about object without two-line elements. Therefore, cooperation already exists.
Yes, but not necessarily open the information.
If you will start our BRICS project, we can fully open this information because our plan to create open database at United Nations level.
Yeah, so that's my point. I mean, the new thing that we can do is to do for the first time open database of these kinds of information.
Information exchange exists now between bilateral, between two countries. Yes. Using our BRICS cooperation, we have enlarged such exchange as minimal for 5 countries, but as maximum for all. Yes.
I just want to make a comment about how important the impact of space debris is going to be on the LSST project when it comes into operation. So at a meeting of LSST in August, it was pointed out that the amount of space debris, the number of sources, very faint, but nonetheless enough to saturate the LSST images, would mean that they will have to avoid observing a large part of the sky at the beginning and the end of the night, which is towards the sun. And that will have a big impact on the way they can conduct the survey, because the simulations they've done have shown that there are enough sources there that are bright enough to completely make the images useless. And so this is something where they've started to talk to some of the satellite companies that are making these small constellations or proposing to make small constellations of satellites. And one of them, which is called Starlink, they have had agreement that they will paint their CubeSats, which are currently just untreated bare aluminium, black, and that mitigates it hugely. But for the other satellite companies, it's not clear, and certainly if, for example, other countries like China plan to put large constellations of microsatellites up, these could have a huge impact on this very sensitive faint survey.
I already cannot understand your question.
I'm just making a comment
very, very long.
that space debris is
I would
going to
like
have a big impact.
Yes, in principle, what is the advantage of our future database, open database for space debris? It may be using for referring as a reference for any astronomical scientific observation. Anybody can input database and understood what is he observed. It space debris or not, или astrophysical object. It returning back to question to complication of international interaction space debris. Explanation is very simple. Only one single country not would like to have international cooperation, Americans. It's a single barrier. Why? Because Americans would like to be single country which has all information for space debris and satellite. Only this reason. Or any another country would like to cooperate, already cooperate, and already in many countries already participate in bilateral cooperation, and multilateral cooperation, etc.
So what you're saying is that there is a political statement that this group can make by putting forward an open network of space debris with an impact, yes?
I would like repeat. United Nations as organization would like to have open the database for space debris. United Nations in
Yes.
all countries.
Yes.
It's
Well,
necessary to make.
yes, of course, but we can be a group that can start making this concretely.
Yes, and if our proposal will be supported by BRICS, we start this work.
Yes, yes. And just another comment for the importance of this. After there was that agreement of the 20 laws of movement of the space, there was an article in The Economist talking about the problem of space debris. So this thing is reflecting. People are paying attention to this.
Thank you for your questions.
Can I have a quick technical question? What's the Yorp effect?
Is the effect is the name of for scientists discovered this effect is the effect of irradiation of solar infrared is infrared radiation re-illuminated from asteroids. It will cause the increase the period of asteroid starting the more quickly rotation up to disintegration.
Okay.
Is the one from reason of appearance of binary, triple asteroid, etc. It's your effect.
Okay. Thank you.
Okay, thank you. I think my question is your last statement where you are saying integration into the flagship proposal. And I wanted to just also maybe get some comments from there. Maybe David and others who are as to how, do they see this in the context of the, optical network?
I mean, I think it's certainly possible that it could be included, this type of network of telescopes under the umbrella of a transient network project with BRICS. The current project that's been put on the table has come from all of the countries where discussions of various science drivers have been presented and cover solar system objects, but not space debris. That didn't come out.
Space debris.
So no one contacted us about... Yeah, and then I think the discussions that I did have with Alexei were about networks of much smaller telescopes that don't need to go so deep and so on. And as I said to him in answer to a question yesterday when I was talking on this, I do believe that it's possible that if there was a will, that we could, encapsulate what you're doing within a BRICS network. They're not mutually exclusive. Of course, we would need to decide where they're going to be situated and who actually is going to benefit from it. Because, I mean, at the moment, a lot of the science drivers for the transient project are things that are of interest to all of the astronomical community, and so far that's not been represented by people like yourself who are interested in what I would maybe not call astronomy as such, because this is sort of man-made stuff. It's not studying science. So it's almost, it's a different sort of arm to, it's a transient, but is it astronomically interesting?
In our presentation, and me and Chen from Parte Mountain Observatory clearly indicated we have all the investigation of gamma ray burst afterglow and asteroids.
Oh, well, for all of those things, of course. Absolutely, I agree.
Okay, last one then.
For those of us who are not familiar with the transient observations, if you share the lead work between the space debris work and the regular, what David called astronomy work, my understanding is the transient astronomy work mostly involves surveys. Surveys means they need as much time as they can get. So how can you share the time on the same network for space debris work, which needs to monitor, and the survey work, which needs a lot of time?
Usually we share telescopes, because for space debris operated only small telescopes. And sometimes these small telescopes, 25 centimeter, 20 centimeter, of course, this telescope also sometimes involved in JRB observation because it's more fast than a larger telescope. It also we have planned to involve such small telescope in asteroids during bright near Earth asteroids. But it not such frequently, maybe a few times per year. But most our telescopes working only for astronomical goals, most large telescope. Therefore, is separated to aperture. All our telescope larger than 40 centimeter, usually using for astronomy.
Okay, thank you, Igor. Our last talk before coffee break is Roberto Soria.
Thanks. So I'm aware that I'm the last speaker before coffee break, so I'll try to keep it within my allocated time. And, I'm going to talk about a project that was already mentioned first day of the meeting by David. I'm going to give a bit more details about it. The project was led is led by Professor Liu Jifeng in Beijing. Jifeng cannot attend this meeting, so it's my honor and my pleasure to represent him here, especially on this such an important day for our mother country. It's a pleasure to be here to give this talk. And as already mentioned in the first day of the meeting, the main goal for this kind of monitoring projects is to detect optical variability on timescales less than a day. So we know very little about optical variability on timescales of an hour, 2 hours, lots of things, flares, bursts, beginning of tidal disruption events and kilonovae and so on, even the first stage of supernovae. So we know much more about things that happen on timescales longer than 1 day. So that's the scientific motivation to set up optical monitoring on timescales of a few hours. For example, you've seen this probably many times. That's the neutron star merger. see this nice light curve, but if you pay attention, all these nice light curves that show the decline of the optical source after the merger, they all start from about 1 day, and we really don't know what happens here when the peak is, and it's crucial to distinguish between different models. It's crucial to have an idea of the first few hours after the burst. So that's why it's important. But I also wanted to show another example that is probably closer to my field of research. This is an X-ray binary. It was observed by Chandra, has a fairly average luminosity of 10 to 38 ergs per second, but then by chance, somebody did a light curve, this paper a few years ago, and right there in the middle, all of a sudden, for a few, maybe 2,000 seconds or so, this thing went from 10 to 38 ergs per second up to 10 to the 40 ergs per second. There's this huge X-ray flare, and then came back down exactly the level it was before. As I say, this was discovered by chance. I have no idea how many other X-ray binaries in nearby galaxies have done that or are doing that or why they are doing it. These are known as ultraluminous X-ray flares. We have no idea what happens there, if it is a tidal disruption of something, how it is possible to increase the accretion rate like this on such a short time scale. Is this some kind of magnetic field reconfiguration? No idea. But clearly this one is an optical counterpart, and it would have been nice to have to find out what happened to the optical counterpart during this X-ray flare that increased the luminosity by a factor of 100. So again, we're talking about time scales of an hour, 2 hours. So let's have a look at what's already available and see what elements we can take and what elements can be improved. The state of the art at the moment, ZTF, Zwicky Transit Factory, they use a 1.2 meter telescope, Schmidt optic. So that's more or less what we also want to use, this kind of telescope, this kind of optics. ZTF is based at Palomar, uses filters in 3 colors. That's good. That's also something we want to do, not just 1 color, but 3 colors. Field of view, 47 square degrees. Okay, that will do. That's something also we can also do. It's almost 4,000 square degrees per hour from this telescope. And the limited magnitude is 20 point something in a 30-second exposure. So that's all good, except that it is 1 telescope. So coverage of the sky is somewhat limited. It cannot do the whole sky too many times. So how can you improve the sky coverage in terms of doing more than 1 scan per night and also looking at northern and southern sky? Well, you do it with many telescopes in a network. So that's the other state-of-the-art facility. That's Assassin. Assassin works with 6 units of 4 telescopes each. So we talk about units. That's something we need to take on board. It's something we need to use for our CTM project. Units are located in Chile, 2 of them, in Hawaii, in South Africa, I think it's the Sutherland, 1 in Texas and 1 in China, Tianshan. So this one, because of these units distributed around the world, can do the whole sky once per night. The problem is that it can only go down to 8 in magnitude because these telescopes are only 14 centimeter aperture. So they're a bit too small. We want something the size of ZTF, but with the concept of units of multiple telescopes like Assassin. And also the other problem is that the pixel scale is 8 arcseconds per pixel, so the images are not going to be great, especially if you want to do multi-band comparison with X-ray astronomy, radio astronomy. If you have pixels of 8 arcseconds, you're going to get a lot of confusion, especially in nearby galaxies. So, okay, we need to take some from here, some from there. What else can we do? Well, NAOC is getting involved with this infrared telescope in Australia. this is part of this galaxy of this project, the growth project led by Caltech astronomers. In addition to the ZTF, there is an infrared telescope at Palomar called Gattini. It's a 30-centimeter telescope. But now there's going to be a better infrared monitor in the southern hemisphere in Australia. It's called GRIMS, J, H, and K band. So NAOC is collaborating on this project. We're trying to learn the ropes in terms of managing data and doing automatic selections of what is interesting, what is not interesting in this kind of surveys. So this is going to be built in Australia. You can see that even a small telescope, 50 centimeters, in a band like the infrared band that is not well covered, is going to do very well. Another telescope used for monitoring is going to be built in China, 2.5-meter telescope wide field survey, developed by the University of Science and Technology of China. 6,000 square degrees per night. Goes down for 30-second exposure. See these colors, goes down to 20-second magnitude. The advantage of this instrument is the coverage in the U-band that many other survey telescopes don't have at the same level. So this one is going to do the northern sky every 3 nights. It's probably the closest thing to LSST for the northern sky for the next few years. It's only 2.5 instead of 8 meters, but it's going to be probably the best thing we will have in the northern sky for this kind of survey in the next 3 to 5 years. It's going to be located somewhere here, up 4,000 meters. I'm told the scene is pretty good. I haven't been there, but they say it's one of the best places in China for this kind of telescope, and this will start in 2023. So there are a lot of things that we are looking at to learn how to do things well, and we put together a few good elements from each telescope, and we try to design this project called CTIAN. We want to do all sky monitoring, north and south. We want to use 1-meter telescopes, not just 20 centimeters or 50 centimeters. We want to use 1-meter telescope to have a depth comparable to the ZTF. But crucially, we want to do a scan every 30 minutes, or maybe 45 minutes. That's going to be the crucial edge of this project. Do it 10 times a night or more to catch variabilities on time scales of 30 minutes or an hour. And also, we want to do simultaneous 3-color imaging. Now, this is very important, especially if you do variability on time scales of 30 minutes. You have a neutron star merger or a supernova, you want to get the colors, you want to know the color evolution. You can't do a sequence of 3 different images in 3 different filters, because between the first and the last image, the colors have changed. So you need to do simultaneous observations in 3 colors with 3 identical telescopes. That's how you get these simultaneous colors. We want to reach 21st magnitude for each scan. We want good image quality, 1 arcsecond pixels, so in any case not much worse than 1.5 arcsecond. We want to be scene limited, if possible. And finally, very important, learning from those other missions, we want to have a spectroscopic follow-up of the most interesting objects. There's not much point in doing a survey for this kind of variable and transient sources and then not being able to take a deep spectrum of the most interesting ones, having to go and hope that there is a telescope available somewhere. So you need to have larger telescopes connected to the same imaging monitoring project, ready on standby to do the spectroscopy of the most interesting sources. So that's the whole package. That was our goal. Project is called CTIAN. In the first phase, we want to have 72 1-meter telescopes, most of them in China, but already starting to put some of them in other countries so we can cover the whole sky, north and south. So I repeat that, 72 1 meter telescopes. They will be divided in units of 3 telescopes each. Then in CITIAN 2, Professor Liu Jifan is even more ambitious. He's already thinking of having another 72 or even more. But first, let's get to phase 1 and install the first 72. And they are divided into units, as I was saying. So each unit has 3 1 meter telescopes, as I said before, because we want simultaneous colors. So these are simple telescopes. There are no filter wheels. It's each telescope is observing in a color, in a certain band. So you get simultaneous colors. So you have 24 units, and you're going to put them, maybe 18 of them or so in China, and then some of them scattered in other locations. Schmidt optics, 5 by 5 degrees field of view, has to be fully automated. And we are thinking of doing 60-second exposures. That gives you kind of a good balance between going deep and being able to scan the whole sky in less than an hour. And then 3 4-meter telescopes, part of this project, as I said, almost on standby, ready to do the deep spectroscopic study of the most interesting transient sources. And then, of course, you need the so-called brain, CITIAN brain. You need to deal with the huge amount of data. You need to coordinate all these telescopes and decide what to do, decide when you want to switch from survey mode to follow-up mode of the most interesting sources and so on. That's still under discussion and development. We are looking, for example, at what the SKA is doing in terms of collecting data from the different radio antennae and then bring the data to Perth, to the POSI Center, and see how they are dealing with that. There is a collaboration between NAOC and ICRAR in Australia. So we're still learning from people who have addressed the same problems before us. Obviously, we need to make decisions fast when there is some interesting object and communicate this decision. So it's going to be some kind of control center in the middle here. Then you have the monitoring telescopes here, the 1 meter telescopes. You have the spectroscopic follow-up with the 3 4-meter telescopes there. Then you have the data management part of the activity, and then you have the data processing. Some of this can be done offline, but most of it has to be done on the fly, because based on the data processing results, you then need to decide if you want to continue in sky survey mode, just scan one bit of the sky and keep moving, or you want to switch to a follow-up mode of something particularly interesting that is happening. And then if that is the case, you also need to decide if you are going to activate one of these telescopes for follow-up, and then send your alerts to multi-band facilities and so on. This is just a comparison of a few of these missions, and you see that the advantage of CITIAN is the huge field of view, of course, because we're talking about 72 telescopes compared with facilities that have only one or two. So that's why this is such a large field of view, instantaneous. I just want to, also the other point is that it's going to do full coverage of the sky in 30 minutes or so. And then I also point out, you see, this is LSST, of course, this is the deepest survey for single scans. This is for the integrated, the stacked after, I believe, 1 week. CITIAN, of course, is much shallower because these are 1 meter telescopes, not 8 meters, so it's only 21.5. But if you stack over 1 week, and if you stack the 3 colors, you get to 26 point something, 26.7. So you get only about 1 magnitude shallower than LSST. So it's not too bad. That's, as I said, that by stacking all the data in all 3 colors over 1 week, you get only 1 magnitude. No, I agree. It doesn't work for crisis. It works for the which one? Which one? Why? You stack for 1 week in 3 colors. I didn't model it myself, but no. Well, I would pass. I haven't done the monitoring myself. I got the data from people at NAOC who did the modeling. So I will. Sure. Okay. Thanks. So this is the proposed location of the telescopes in China and in other countries, not just the BRICS countries, because we also need Australia if you want to have a full coverage, and Chile. In Chile, in particular, telescope is going to be located on Cerro Ventarones. Sorry for the pronunciation. It's a location that was given to the Chinese research center in Chile called Casaca. So it's a research center run by the Chinese Academy of Sciences, but located in Chile. And we are hoping that it will be possible in the future to have a similar agreement with Chinese research centers based in other countries as well. So China has some space on the mountain here, not far from these other telescopes, and this is where we plan to put a unit of 3 telescopes. In addition, of course, there is a collaboration with these other countries. I'm not going to spend much time on that. Most of these meetings and memoranda of understanding happened before I moved to China, so I wasn't directly involved in any of these meetings. I can probably recognize someone here. There's definitely, I can recognize Ross there, I think, from the picture. That's you, right? Yeah, it's very, very easy to spot you there. And I'm sure David is somewhere in one of those meetings. Right. In addition to South Africa, Spain, there is a memorandum of understanding with the Canary Islands for the telescopes in the Canary Islands, so China can use that telescope. Australia, in Australia, Siding Spring. So we are hoping to put one of these units at Siding Spring. There is a collaboration, bilateral collaboration between China and Australia. Every year there is a meeting called the ACAMAR meeting. This year it was in Australia, next year it will be in China, and so on. So this is a bilateral collaboration. I'm not going to spend much time on the technical details. You can ask me later because it's not particularly interesting. Just remind you the mirror is 1.3 meter. 80% of the encircle energy will be 1.4 arc seconds, and the pixel size is 1 arc second. So that's just the kind of image that we want for these telescopes. We still haven't decided officially whether we're going to use CCDs or CMOS detectors. Initially, we were thinking CCDs. It was going to be a mosaic of CCDs to get a field of view of 5 by 5 degrees. But we thought, well, it seems that 10 years from now, so-called scientific-grade CMOS detectors will be more competitive, will be more efficient than CCD. So that is probably what we're going to use. Just for those who are not familiar with this thing, well, a CCD is usually read out. When you read out a CCD, you cannot take any data. You need to. You have a shutter, so for a few seconds, you have to read out all the data from the various pixels, and then you take a new image. So there is a global shutter, and then you waste time to read out your CCD. For CMOS, you have an ADC analog to digital converter at the end of each column, and you can essentially read out row by row. You're transferring charges down row by row, and you read one out, and then you remove the charge, you move down the next row, and so on. So you have like a rolling shutter, but you can keep collecting data while the next row is being read out. So that gives you more efficient use of your time. Of course, there are many other differences that we need to take into account. CCDs have higher quantum efficiency, and it's a mature technology. CMOS is going to be cheaper, we think, in 5 to 10 years' time. They have a lower readout noise, faster readout, longer life because there's no mechanical shutters that can break down, lower power consumption. That's particularly important for countries where electricity is so expensive, like Australia. And also, CMOS are actually, technology is actually driven by mobile phones. So every time in China we take a selfie or a picture of what we've had for lunch or dinner, we are contributing to astronomy in a way by developing the CMOS technology. So we think CMOS will be the way to go. You can look at the table later after my talk. There's plus and minuses of the different things for CMOS and CCDs. Technical aspects of the telescopes. Again, I'm not going to waste much time on this. I'm just going to say that these are the 4-meter telescopes. So there's going to be a Cassegrain focus and azimuth focus, and these are the pointing accuracy and so on. It's not particularly exciting to look at these lights. It's a fairly standard imager and spectrograph on the 4-meter telescope that is going to be used for follow-up observations of the most interesting sources. This is, again, on the 4-meter telescope. There's going to be a dichroic here. You can split the light into green and red channel, and then you send the infrared down here, so you can actually go down in the near infrared as well. And then this is the optical path of the spectrograph. So these are the goals. Just to summarize at the end of my talk, we want to get optical counterparts of gravitational wave events, and then all the other astrophysical variables and transients, especially early evolution of supernovae. We also think we can do exoplanets, microlensing, near-Earth asteroids, stellar flares. There is an interesting research group at NAOC looking at spectra of Milky Way stars with LAMOST, 4-meter telescope, in conjunction with the TESS and the Kepler studies. So stellar flares is an interesting line of research at NAOC. It's also interesting because you want to understand the concept of habitability zone in planets. So you want to know exactly how stars flare up and possibly destroy atmospheres in planets. And then all sorts of other variable sources. This is timeline. The next 5 years, we are discussing the technical properties of the CTN project. We are funded to do this technical design phase and testing. We're obviously not fully funded to build the whole thing. That will be the next 5-year plan. But next 5 years is the design phase. And then late 20s, 27, 28, we're going to start building the first units and proving that they work. And then we think that we can complete an installation of all 72 telescopes around 2030, and then full scientific operation from 2032. This is the kind of cost we're looking at. Whole network, $300 million for the 72 1-meter telescopes, about $100 million for the 3 4-meter telescopes, and then about $60 million to do the brain, the computing facilities. And these are some of the things that are still being discussed in terms of testing and developing, getting technology ready, deciding exactly what limiting magnitude we want to get, again, develop the CTM brain, decide which optics we want and which whether we want CMOS or CCDs. It's not the only scientific project led by NOC in terms of monitoring. In my last couple of slides, I just want to advertise another project based on all-sky monitoring, this time in the X-rays. And this is called Einstein probe satellite, also developed at NOC. You're all familiar with eROSITA. eROSITA is doing this nice survey of the sky, but the point of Einstein probe is to do it fast, to do it many times a night. That's why we're using a technique called lobster eye optics. It's not a Volter type mirror. It's a grid where the X-ray photons bounce off the walls of this grid and then they give you this kind of image. So image quality is not great, but it gives you a huge field of view that you can use to do an all-sky monitoring every 6 hours. So you're going to get a lot of X-ray transients that then you need to follow up with optical telescopes. CTN is not going to be operating probably during the lifetime of Einstein probe. Einstein probe is only going to be operating probably between 2023 and 2028. But there will be a lot of other ground-based missions that can work in conjunction with Einstein probe. So I'll conclude. I'll finish here. If you want to get in touch with NOC about this, and you can contact Professor Yuji Fang. And ideally, it'd be great if we can merge or make sure that we work together with the optical transit network within the BRICS framework. And so I'll thank you for your attention.
Okay, thank you. Since we ran out of time, I have just one question for Dimitri that raised quickly his hand.
The current status is we're funded for the next 5 years to do all the technical development and testing. So between now and the 2024, we will decide the type of telescopes, the optics, the detectors, and then finally, within the next 5 years, build the first prototype unit with 3 telescopes and install it. And then show, and then we can see what limited magnitude we get, and so on. And once this is done, for the next 5-year plan, you know, a country like China likes to operate in terms of 5-year plans, then it will be time to install all the 72 telescopes. I'm optimistic because I see that the Chinese Academy of Sciences has been quite successful in obtaining a lot of research grants from the government. And as you know, they built the FAST radio telescope. It was huge. And that gives Chinese Academy of Sciences some kind of credit in terms of, you know, credibility with the government to get a lot of investments to do something on these scales in terms of optical. And the Chinese government is very keen on developing a large-scale project, including this kind of international collaborations to show the global dimension of Chinese research.
Okay.
Yes, absolutely. That's why we, you know.
Okay, thanks, Roberto. We are now heading to the coffee break. Thank you.